My name's Matt Engel. I'm a postdoc in the Lab for Electromagnetic and Electronic Systems here at MIT. I reside in the basement of Building 10, where I work for Professor Jim Kirtley. Kirtley had class this morning, so you get me. So, brief outline, tell you why we're doing this, what we're doing, and what we're going to do with it. The original problem that we were looking at solving was detecting fault currents in distribution systems. Basically, an electrical fault involves a component failing and current flowing through it. More practically, it results in fires. If you have a fault, something is either burning or about to burn. So we'd like to be able to detect this and throw a breaker, stop electrical current, put out fires. On the other side, there's some work that's taken place in our lab in Professor Stephen Lieb's group called the Non-Intrusive Load Monitor. And these guys have taken current and voltage sensors and applied them to the electrical mains coming into the lab. And what they do is they look for electrical signatures on the lines in the current and voltage waveforms, and they're able to identify individual electrical loads. For instance, they can see the cycling of the motor in the refrigerator in the lab. They can see the microwave turn on. They've even gotten good enough that they can see individual electric or fluorescent light ballasts turning on and off. So with all that information, they can feed the big data machine, and they can chart all of the going-ons in the lab. You know, they can tell what time I've come in, when I've started up my computer, and even when I've had the processor in my machine running hard doing computations. So that can be a good or bad thing depending on how you want to look at it. So to do that, we need good current sensors. Voltage sensors are easy, current's much harder. Current solutions are large and expensive. Currently, well, so the obvious way to do this, you look at the magnetic field surrounding the current carrying wire. Ampere's law tells you what the magnetic field surrounding a flowing current is going to look like. So you can measure it and then back out the current flowing in the wire. I guess the first way to do this is people will put a ferromagnetic core surrounding a wire, basically build a single turn transformer on the primary, and then wrap a sense wire around the magnetic core. And that way they will, they'll read the current in the wire. The trick is that doesn't work for direct current. You can't see direct currents on that because they very quickly saturate the transformer. So people move to other technologies. They'll use Hall sensors. They'll use, more recently, optical-based solutions. And an optical-based solution can be either a magnetostrictive material, a material that shows strain when it's exposed to a magnetic field, something that can be read optically. We also use, there are different electro-optic effects, and those are commonly used. They're often bulky and a pain to install. You can see on the right, that's one of the common sensors in the industry. It's installed around a bus bar. So what we're doing is we use an effect called the Vaad Effect. It's basically a property of certain semiconductor materials, crystals. Gallium manganese arsenide is one example. The material is anisotropic, which basically means that light polarized in different directions corresponding with the axes of the crystal moves at different speeds. So the polarization of the light is changed as the light goes through the material. And this effect changes based on the magnetic field that the crystal is exposed to. So based on that, we change the polarization of the light as it moves through. So what do we do with that? Well, we build an interferometer. The flux generated by a current changes the optical medium. We use two paths with linearly polarized laser light. One's a reference path, one is a path through this material. The path through the material, the polarization is changed by the magnetic field. And then we recombine these two beams of light. We look at the interference patterns, and from that we can back out the magnetic field, and then from there the current. The neat thing is this effect has a huge dynamic range and is very sensitive. We can measure fields down to what is it? 10 Gauss, which is about 20 times the Earth's magnetic field. So we're sensitive, we have a high dynamic range, we can see very, very small currents on top of large carriers, and the really neat thing is that it's scalable. We can scale it down, we can put it in an integrated circuit. So instead of surrounding a wire with a large iron core, we can just take one of these little chips and put it on the side of the cable, and knowing the cable geometry where it's sitting, we can very accurately pull out the current in the wire. And we can do with that what we like. In any case, thank you very much. If you want to know more, come see me. I have a poster.